Good afternoon, everyone. My name is Wei Yu. It's my great honor to present our research work, ProFuzzer, an on-the-fly input type probing technique for better zero-day vulnerability detection. This is a joint work from Purdue University, Indiana University, and Renmin University of China. Actually, I found that it doesn't work. To move to the next page. Oh, okay, it works now. And first, let me give a brief introduction to the mutation-based fuzzing. It starts from a set of valid input instance as seed input and continuously modifies them to explore various execution paths. And in each fuzzing iteration, an input is selected from the seed corpus for random mutations, and the mutated inputs are executed on the target application, and their code coverage are traced. And those mutated inputs that increase code coverage are saved into the seed corpus for further mutation. But unfortunately, blindly random mutation is not that effective. We use AFL, the most popular mutation-based fuzzer, to fuzz OpenGPAG for 24 hours. And we observe that more than 60% of the mutations are performed on the input bytes that are ineffective. As presented in this figure, whose x-axis labels each individual byte of the input, and the y-axis shows the number of mutations performed on each byte. So here we observe that more than 1.5 million mutations are performed on the 31st byte, which is ineffective for coverage improvement. And another observation is that the effective mutation ratio drops very quickly. The effective mutation ratio is measured by the number of mutations that increase coverage over the number of total mutations. As presented in this figure, whose x-axis stands for the hours spent in fuzzing, and the y-axis stands for the effective mutation ratio changes around time. And we can see that the code coverage is hardly improved after 8 hours. And the existing works improve fuzzing on both breadth and depth. On the one hand, different seed selection and prioritization algorithms are proposed to help cover as more program code as possible given a limited budget. And on the other hand, multiple program analysis, such as TAND analysis, symbolic execution, and gradient-based search, are proposed to integrate it with fuzzing to reach program paths that need to satisfy a specific condition. So this work has improved the effectiveness of fuzzing to some extent. However, some more highly effective fuzzing requires in-depth knowledge of the target program's input. So this motivates our work of ProFuzzer, which performs an on-the-fly input structure understanding and utilizing in a two-stage fuzzing process. So in the first stage, the types of the input fields are probed in a lightweight manner that consists of 3 steps, including per byte mutation observation, field identification, and type discovery. And in the second stage, the type information is leveraged to explore valid values for better code coverage and exploit specific values that may lead to a vulnerability. So we should note here that the types discussed here are application agnostic types, such as raw data, size, which are critically important for fuzzing, instead of those application-specific types, such as IP address or PDF data structures, and so on. And we identified 6 fuzzing-related input types, including assertion, raw data, enumeration, offset, size, and loop count. And these types cover most of the input content for popular applications, and each of them affects a program execution in a unique way. So we take enumeration and size as examples. An input field of enumeration type has a small set of valid values, with other values causing the program to terminate with exception. Here we show a code snippet of OpenGPAG for assessing an enumeration field that indicates the color depth. As we can see that OpenGPAC supports 4 different color depths, each corresponding to a different handling function. And input field of a size type determines the amount of data the program should read from the input for further processing. So here is the code snippet from OpenGPAC for processing a size field that indicates the image height. So as we can see that the program will terminate directly if the input file is not lengthy enough as indicated by the size field. So input fields are automatically discovered via byte-wise mutations and analyzing the impacts of the individual mutated bytes on the program executions. So specifically, given a seed input, ProFuzzer mutates 1 byte at a time, enumerating all the 256 values of the byte to collect the corresponding execution profiles. So an execution profile is the trace difference between the execution with the original input and the execution with the mutated input. And after observing per byte mutation effect, we group consecutive bytes that share similar execution profiles together as an input field. For example, the 0 and the first bytes compose a group since they share similar execution profiles, while the second byte starts another group since its execution profiles are totally different from the previous bytes. So the intuitions behind this net, the program tends to perform a validation check on a whole input field instead of individual bytes. Hence, if consecutive bytes belong to a same field, it is very likely that they share a large part of their execution profiles that corresponding to invalid mutated values. As an example, the zeros and first bytes of the input are simultaneously checked by simultaneously examined by a check against a constant value. Here we show the profile similarity graph of these 2 bytes, whose x-axis enumerates all the possible values for the byte, and the y-axis shows the similarity between the original execution and the mutated execution. As we can see, both bytes has only one valid value whose corresponding similarity score is 1. And the other invalid values to lead to the termination of program has a very low similarity score. So these 2 bytes share the same minimal similarity since they have the same termination path with the exception. So we group them together. Then given a group of consecutive bytes as an input field, the next step is to determine the type of the field. Once again, we use the enumeration and size as examples. And for an enumeration field, there exists a proper subset of all its possible values, such that for any value in this subset, its similarity score is larger than the mid-range, and for any others not in the subset, its similarity score is smaller than the mid-range. So as shown in the profile similarity graph of the 28th byte, which is an enumeration field, there are 4 valid values that may lead the program move forward, hence have a relatively high similarity score, while other invalid values lead the program terminate immediately, hence the similarity score is very low. Now let's move to the field size field. So for a size field, there exists a bound such that different values within the bound corresponds to different similarity scores larger than the mid-range, and for any value beyond the bound, its similarity score is smaller than the mid-range. So as shown in the profile similarity graph of this 22nd byte, which is the size field, note that value 2 is the bound, as we use a very small image as the input, and the value smaller than the bound have a relatively high similarity score, since the input is lengthy enough that then the amount of data should be read for further processing. And while the values larger than the bound have a very small similarity score, indicating early termination. So by matching execution profiles with different feature patterns, the type of each field is identified. We use different legends to mark different types of fields in this figure. As we can see, we have 6 kind of types of fields that are identified. And the type information is used for guide further mutations. The guidance is provided in two aspects. In the first aspect, it limits the mutation to all the valid values of the field type to achieve better coverage. As an instance, for a size field, when mutation increases its value by x, it also appends x bytes of data at the end of the file. And in the second aspect, ProFuzzer exploits a set of special values that may lead to potential vulnerability. As an instance, for a size field, we will try to force its value to be the difference between the end of file and the current location, which may result in buffer overflow if the program does not properly handle unexpected values. And we conducted a set of experiments to evaluate the effectiveness and efficiency of ProFuzzer. Due to time limit, we will present 4 of them here. So the first one is the probing accuracy, which measures whether ProFuzzer can correctly identify fields and their types through probing. We acquired the ground truth by manually checking how applications handle individual bytes and then compare the probing results with the ground truth to measure false positive rates and the false negative rates by ProFuzzer. We also compare ProFuzzer with AFL analysis, a simple offline file format analysis utility included in AFL. So the evaluation result shows that ProFuzzer has only around 5% false positive rate and false negative rate on average, while AFL analysis has around 40% false positive rate and 70% false negative rate, which is relatively high. And the second one is finding zero-day vulnerabilities. We run ProFuzzer on 10 extensively tested real-world applications. These applications cover different categories, including image, audio and video, PDF, and compression. So within 2 months, 42 zero days are discovered, with 30 of them awarded by CVE. The third one is the evaluation on standard benchmarks. We compared ProFuzzer with some state-of-the-art fuzzing tools, including AFL Fast, Jiller, and Fuzzer on Google Fuzzer test suite to see whether they can reach the specified code locations. And the evaluation results show that ProFuzzer can reach more target locations and is 2 to 8 times faster than other fuzzers. And the fourth one is the performance compared with other fuzzers. So as we can see that ProFuzzer achieves more pass coverage than other fuzzers and spends less time to reach the same coverage. Besides, ProFuzzer keeps relatively high effective mutation ratio. Finally, we discussed the differences between ProFuzzer and closely related works. Some early studies reverse engineer the input structure at an offline fashion by using symbolic execution, type propagation, or memory access pattern analysis. And recently, researches on field-aware fuzzing are emerging. They intercept string comparisons or perform 10 analysis to infer magic value bytes, perform the type, program type, and the shape and size of the input types. And different from these works, ProFuzzer includes a lightweight mechanism to discover the relations between input bytes and program behaviors by observing the program execution paths violations in response to mutations of this input content. So instead of using a heavyweight program analysis technique such as tagged analysis or symbolic execution. In addition, the inferred type by ProFuzzer is application agnostic and fuzzing related instead of the program specific. So in conclusion, we propose a technique that leverages on-the-fly type learning to improve fuzzing. The basic idea is to probe input fields and types by observing the fuzzing process and leveraging the type information to explore more program passes and exploit the potential vulnerabilities. Based on the proposed technique, we implemented a prototype system called ProFuzzer. And the evaluation results indicate that ProFuzzer has a better performance of both code coverage and vulnerability exposure. It discovered 42 zero-days vulnerabilities, 30 of which are assigned with CVEs. The source code of ProFuzzer will be released soon on the GitHub. And that is the end of my presentation. And thank you for your attendance, and I'm happy to take any questions. Thank you.
Use the microphone and state your name and affiliation.
Sure. Cristina Nițerotaru, Northeastern University. So first, an observation, there is some work in fuzzing protocols, myself included, where we actually use types in order to speed up, coverage, speed up and also improve coverage. But my question is, you show that your technique improves over several other fuzzers. Do you have any idea where is that improvement coming from? For example, you were identifying several types. Maybe all your improvement comes from one type. The
improvement comes from two aspects. The first aspect is that we ignore or eliminate some unnecessary type mutations on that those bytes whose mutation is not ineffective, such as raw data or assertion, because that any mutations on these 2 bytes has no helpful for improve the coverage, right? For the raw data and the assertion. And then the other aspect comes from we focus our more effort on fuzzing on mutation with those validated value. So for example, for the enumeration field, we only mutate them with the valid value that will make the program move forward, and we don't fuzzing with we don't mutate with that invalid value that will cause the program terminate immediately. So I think the improvement comes from these two aspects. One is ignore those ineffective mutations. The other is focus our mutation on those effective ones.
Okay,
thank you.
Nice work. I'm Jing from Stevens. So I saw you compared your work with tensor analysis-based works like Angora. Do you have any evaluation comparison between ProFuzzer and Angora? I do understand that when your paper is accepted, Angora may not be open source at that time. But do you have evaluation results by now?
Yeah, thanks for the suggestion. And this suggestion is also the one that our reviewers suggest us to do. But at the time of writing of this paper, that Angola is not released. So we have asked for the authors, and then they say that they have released them recently. So we haven't get time to compare our tool with the Angola. And I think we will just start to make it as our future plan to compare them. Yeah,
thanks for the information. Just one more sentence. So the tensor analysis in Angora is quite efficient, actually. So you may want to give it a try. Thanks.
Okay, thank you.
We're out of time. Let's thank the speaker again.
Thank you.